So dear students, welcome to the unit number 2. Now in this unit number 2, we are going to study a different kind of stereoisomerism. We will study geometrical isomerism and conformational isomerism. In the geometrical isomerism, you will study different types of isomers like cis-trans isomer, EZ isomerism, and in conformational isomerism, you will study what conformers are. You will study the conformations of ethane, butane and propane. Moreover, you will also study about partial and asymmetric synthesis. So without making much delay, let us move for our unit number 2. We will study geometrical isomerism first. So we must know what geometrical isomerism is. So if I ask you, just there is a carbon which is attached to a single bond with another carbon, and if I ask you to keep this carbon fixed and rotate this carbon around the single bond like this, so can you rotate it? Yes, you can rotate it very easily. But if let's say this carbon is doubly bonded to this carbon, okay, or let's say these two carbon are in a ring. Now if I ask you to rotate this carbon keeping all the two other carbons fixed, say let us say keep this carbon fixed, okay, this carbon is fixed and I want you to rotate this carbon, okay, or in this molecule I want you to fix this carbon and rotate this carbon around the double bond, okay. So if you try to rotate this around the double bond or around the ring, it will become very difficult for you to do the same, okay. Why? Because you see that there is a restricted rotation around the double bond or the plane, okay. So there is a restricted rotation around double bond or the plane, okay. So because there is a restricted rotation about this plane, so it gives rise to two kind of orientation, two type of configuration. Let's say this carbon is attached with one hydrogen and with one OH group, and it is doubly bonded to another carbon which is also attached to one OH group and one hydrogen. Now there could be another orientation in which this carbon is having H and OH likewise as the first carbon, but the OH on this side will now go opposite to the OH and H will be opposite to the previous carbon H. Now you see here that these H and these OH are on the same side of double bond, whereas in this molecule this H and this OH are on the opposite side of the double bond. Now due to this condition, you see that these two are having same molecular formula. The first one and the second one are having same molecular formula, but you see that these two are having different configurations, different configurations, okay. Their relative arrangement in 3D space is different, okay. So hence these two are known as geometrical isomers. Why they are geometrical isomers? Because they are having the geometrical isomerism arises due to the restricted rotation around the double bond or the plane. So due to restricted rotation we can get two orientations, two types of isomers. Now the first one in which OH group are on the same side is known as cis isomer, and the OH group which are on the opposite side of the double bond are known as trans isomer. So this is first geometrical isomerism is. Geometrical isomerism also can be checked in a plane. In the plane, how will you see cis and trans? In a plane, if let's say this carbon is attached with a CH3 and an H, this CH3 is above the plane and this H is below the plane. Now if there is another CH3 above and H below the plane, now these two CH3 are on the same side of the plane and hence they will be termed as cis. Whereas if we are having two CH3 in which one CH3 is above the plane, H is below the plane, and another in the other carbon CH3 is below the plane and H is above the plane. Now you can see that these two CH3 are on opposite side of the plane. So hence these two are known as trans isomer. So this is how cis and trans isomers and geometrical isomerisms are seen, are understood. Now we will see the definition of geometrical isomers. Okay, so what is the definition? The definition says that isomers which have the same structural formula but different relative spatial arrangement of atoms or groups in groups around, okay, groups around the double bond are called geometrical isomers, are known as geometrical isomers, and such type of isomerism is known as geometrical isomerism. Okay, so such type of isomerism is known as geometrical isomerism. Okay, now in the previous videos of the unit number 1 I have already told you about that geometrical isomers are also configurational isomers. Okay, they are configurational isomers. And what configurational isomers are? Configurational isomers are those isomers in which one isomer can be converted into another by breaking and reforming of the double bond. Let me revise you it again, that we are having cis isomer of this molecule and I want to convert it into trans isomer. Okay, I want to convert it into the trans isomer. So this trans isomer, formation of this trans isomer cannot be done directly because there is restricted rotation around the double bond. This one is cis and this one is trans. So what we are going to do is we will break one of the bond, double bond, carbon carbon double bond. That means we will break the pi bond between carbon carbon and we will convert this into carbon carbon single bond. Okay, we will convert this into carbon carbon single bond and then we will do the rotation. Okay, say this H is here, this OH is here, this OH is here, this H is here. First we will break the double bond and convert it into single bond, then we will rotate the molecule keeping one atom fixed. We have to keep it fixed and we have to rotate this one. Now when we will rotate, we will get the OH on opposite side and then we will reform the double bond of it, and this is how we get trans isomer. So because conversion of one isomer into another requires breakage and formation of double bond, hence these are known as geometrical isomers. These are known as conformational isomers. Okay, sorry, configurational isomers. Okay, now we will see what is the necessary and sufficient condition for geometrical isomerism. This is a very important thing that we must know, that in order to show geometrical isomerism, what is the necessary and sufficient condition. So the necessary and sufficient condition to show geometrical isomerism. Okay, so first of all, the molecule must contain a double bond. Okay, there must be a double bond. So molecule must contain double bond. First of all, the very important thing. Okay. Point number 2. When in the geometrical isomerism, the carbon atom, okay, the carbon or the atom which we are stating must have two different group. Okay, it must have two different group. A carbon which is attached to the double bonded with the another carbon cannot have same group. Means for example, if you say that this is A group attached to it, this one is also A attached to it, but this is B and this is C, then okay, or maybe or you can say that this is A and this is C. This is wrong. This will not show geometrical isomerism. Because why? Because the two groups on the carbon are same. This cannot happen. Okay, can this happen where a carbon is having a group A and B on it and it is doubly bonded to another carbon having group A and group B on it? Yes, this can happen, and this will show the geometrical isomerism. It doesn't matter whether these two carbon can have same groups or different groups. They can have both the same groups, like the first carbon is having A and B on it and the second carbon is also having A and B on it. It can be possible, but it is not possible for these two carbons, the only one carbon having same groups. So this is possible, and particularly you understand that A and B are on the opposite side. So this is our trans. Now this can also show geometrical isomerism. C double bond C. This is A, this is B, and this is A, this is B. This can also show geometrical isomerism. This is our cis form. Okay. Okay. Now there is one more thing to understand. Okay, now can this be possible? Can this show geometrical isomerism? C double bond C, A and B and C and D. Yes, this also shows geometrical isomerism. Although four groups are different, but yet yes, they will show geometrical isomerism. In particularly, we will not name them cis and trans. We will name in the form of E and Z, antigen and Zusamen. This can also be possible. Okay, and we will see how to nomenclate them in our next video. Okay, now there is one more important thing. The important thing is that these carbon atoms which I am talking about, we have to see that the groups attached to this carbon has to be same side on the double bond. Now when I talk about same side, it means that take condition like this. Consider it a plane, and along the length of carbon-carbon double bond, one must be on, this is side number 1. Okay, this is side number 1 and this is side number 2. So please understand that same side of double bond means along the length of the carbon. If you imagine a line, a straight line or a plane, so either side of the plane are two sides. So if a compound is cis, so that means both the groups on different carbons are on the same side or on only one side. Like for example, in this case, these two groups are in the side number 2, or these two groups are in the side number 1. Okay, but when they are trans, the similar groups, or one of the group in one carbon is in side number 1, and the same group, the identical group on the other carbon is on the other side of the group. So this thing you must understand, that when we talk about same side of the double bond and opposite side of the double bond, what does that mean? Okay, now if I ask you a question that about, say for example, can this show geometrical isomerism? CH3 H double bond carbon H and H. So if I ask you, can this molecule show isomerism, geometrical isomerism? The answer is no. This will not show geometrical isomerism. Why? Because this H and this H are these are the two identical groups on the same carbon atom, which must not happen. So I hope you have understand that what is the necessary and sufficient condition to be a geometrical isomer. So this thing is very important, a very basics, and you must all know about it. Okay, now geometrical isomerism, you have seen till now that you are seeing geometrical isomerism either in alkene, okay, or in a plane. Okay, so till now I have told you that geometrical isomerism can be seen in alkene or a plane. Let me give you some examples of plane as well, because I have already given you the example. So let me elaborate on it and give you few examples more. See this one, cyclopropyl group having HCOH on one side and HCOH on the side. Now you can see that these two COOH are on the same side of the plane. They are below the plane. Both are below the plane. While in this molecule HCOOH is in this COH is on below the plane, while this COH is above the plane. So this is acting as trans, whereas this one is acting as cis. Okay, so these two groups are on the opposite side of the plane. This is one example, and one more example you can take to understand. Okay, this one is cyclopentyl group, and this is HOH, and this is HOH. Now you can easily tell me and understand that this is a kind of cis isomer, because the two groups are on the same side of the plane. They are both below the plane, while in this HOH and OH and H are on the opposite side of the plane. The similar groups are on opposite side of the plane, hence they are acting as what? Trans. Okay, so these are the few examples of compound showing geometrical isomerism in cyclic molecules. Now we can also see geometrical isomerism. We can also see geometrical isomerism in oximes and azo compounds. Now in oximes and azo compounds, geometrical isomerism can also be seen. Okay, how? Let's see. Let's take the example of oxime. Now what is an oxime? First of all, you must remember this in your mind. For example, I am having C6H5. okay, we are having benzene ring, benzaldehyde. Let's say we have benzaldehyde. Okay, now I react this benzaldehyde with hydroxylamine, NH2OH. Now when I react with hydroxylamine, I see that a carbon double bond nitrogen is formed. Okay, carbon double bond nitrogen is formed, in which nitrogen is attached to a hydroxyl group, and okay, this carbon is attached to the same hydrogen, and a new carbon nitrogen bond, double bond establishes, in which nitrogen is attached to the OH group. Now this molecule is called as oxime. Now what happens in oxime? This oxime is also able to show geometrical isomerism. Why and how? See, first consider that this nitrogen is having a lone pair of electron, which can be understood, which can be taken in mind like this. It can also be taken as a group. Okay, nitrogen is having sp2 hybridized orbital, and this electron pair is lying on this sp2 hybridized orbital. Now you can see how it similarly looks like the above compound. Okay, so this oxime is also able to show that geometrical isomerism. How? See, you can see that these two, this molecule can also be represented as like this, or maybe you can you can draw another isomer of it like this. This one is benzene ring, carbon, single bond hydrogen, double bond nitrogen, whereas when this OH is on the left hand side and this electron pair on the right hand side. Okay, so first of all, why this molecule is showing geometrical isomerism? The answer is simple, straightforward as previous, because there is a restricted rotation around the double bond. Rotation is not possible, hence it is showing geometrical isomerism. Now what are the two geometrical isomers? The two geometrical isomers are in which OH group is on the right and in which the OH group is on the left, or you can say lone pair is on the right side and lone pair is on the left hand side. Okay, so these two will show geometrical isomerism. Now what is the name given to these geometrical isomerism? So let me tell you that we do not use cis and trans for designating geometrical isomerism in oximes. No, we don't use it. We use syn and anti. Okay, we use syn and anti for these things. Okay, okay, now the question is, what is syn and what is anti? So syn name is given to those oxim in which OH and H group lie on the same side of the double bond. So this one is, the name of this compound is syn benz aldoxim. Okay, and as because in this one molecule the H and OH group lying on the opposite side, we will use the word anti-benz aldoxim. Okay, so this is how syn and anti are named. Syn, in syn, H and OH will lie on the same side of the double bond, and anti, H and OH will lie on the opposite side of the double bond. Now there is one more interesting thing you to note, and I hope you understand that oximes can be prepared by both aldehyde and ketone. You can use an aldehyde like benzaldehyde, okay, to prepare an oxime by reacting it with NH2OH. So now you see that two kind of oximes are formed, C double bond N OH H, okay, and C double bond N OH and H. Okay, so two kind of isomers are formed. You know that, sorry, let me draw this diagram again. Now you see that this one OH and H on the same side, this one is syn and this one is anti. Now we can also form ketone. We can also form this oxime with a ketone, because why am I saying this? Because in ketone you will not have H. You may have another group, maybe CH3, maybe C2H5. It doesn't matter. So we are not having H. Now how will you identify the syn and anti oxime in ketone formed from ketone? Okay, so let us say we are having acetophenone and we are reacting it with NH2OH. Okay, so we are having acetophenone and we are reacting it with NH2OH. So when we are reacting this acetophenone with NH2OH, okay, then we see that there is a double bond N. Okay, now you will see that there is a electron pair and OH. Okay, you may get OH and CH3 on the same side, and you may get OH and CH3 on the opposite side. Okay, so this is very interesting thing to understand. But how will you say which one is cis and which one is syn and which one is anti? Now in order to give syn and anti term, we should see the IUPAC nomenclature of it. For this one, the molecule is methyl phenyl ketone. Methyl phenyl ketoxim. Okay, the molecule is methyl phenyl ketoxim as per the IUPAC nomenclature. As because methyl is coming first, now we have to see the first name that is coming. Okay, the first name is methyl. Now then we have to see whether OH is on the same side of methyl or opposite side. Now as because OH and CH3 are on the same side, we say that this one is syn, whereas in this OH and CH3 are on the I'm sorry, I have changed the configuration. Let me draw it again. Okay, let me draw it again. Okay, so let's see this again. So OH is there, so OH is here, and lone pair of electrons are here. Okay, and C6H5 and CH3 are as it is, they were fixed, and OH was rotated. Now you see that this OH and CH3 are on the opposite side of the double bond, hence they will be termed as NT. Okay, they will be termed as NT. So NT methyl phenyl ketone. Now this is how we see the cis and trans isomerism in, or geometrical isomerism in oxime. Now there are another compound, another set of category of compound which show geometrical isomerism, and they are called as azo compound. Okay, so let us see an example. For example, we are having azobenzene, which is one benzene attached with a nitrogen. This nitrogen is attached to the double bond with another nitrogen, and this nitrogen is again attached to benzene ring. Now each two of these nitrogen are having lone pair of electron. Okay, so these two are having lone pair of electron, and they are known as syn. Okay, now how will you give them name syn and NT? You will, first of all, you must know that the name syn and NT will be given here. There will be no cis and trans. It will be same as that of oxime. Now how we will give them name? So first of all, we should draw the structure. Okay, okay, now what we will do is we will see that this is C6H5. I will draw benzene as C6H5, and this is N, double bond N, and C6H5. Okay, and the lone pair and the lone pair. Okay, so lone pair are on the same side, which will be called as syn, whereas if lone pair are on the opposite side of the double bond, like this one is lone pair here, and this one is lone pair here, this one is C6H5 and this one is C6H5, hence it will be known as NT. So this is how syn and NT are done in the azo compounds. So I hope you have understood what all these means. You have understood the basic condition of geometrical isomerism, basic understanding of geometrical isomerism. Now in our next video we are going to learn then what are the physical differences between cis and trans isomers. Okay, thank you so much.